Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Wireless performance is not just a matter of bandwidth or signal strength. It starts with design. How you place access points, choose antenna types, and manage wireless channels directly determines whether users experience smooth, reliable connections or suffer through dead zones, disconnects, and slow speeds. Too often, performance issues stem not from misconfigured settings, but from poor physical layout and signal interference. When access points are placed carelessly or without consideration for their environment, even the most capable wireless hardware cannot perform at its best. Troubleshooting wireless effectively starts with understanding these physical and environmental variables. In this episode, we focus on the practical aspects of wireless design, antenna placement, channel selection, and the causes and effects of signal loss. Whether you're planning a new deployment, diagnosing coverage issues, or reviewing for the Network Plus exam, understanding these fundamentals is essential. Many wireless problems trace back to improper planning, and this episode is dedicated to helping you identify and correct those root causes. Let's begin with antenna types and placement basics. Most access points use either omnidirectional or directional antennas. Omnidirectional antennas radiate signal in a 360-degree horizontal pattern, ideal for open floor plans or central ceiling placements. Directional antennas focus the signal in a specific direction, useful for long hallways, warehouses, or connecting distant buildings. Antenna choice depends on your coverage goals and the environment. Wall-mounted APs may have antennas angled downward, while ceiling-mounted APs provide top-down coverage. The physical mounting position should be chosen with the device's radiation pattern in mind to ensure maximum coverage and minimal waste. Common placement mistakes include putting access points too close together, leading to excessive interference and channel contention, or placing them too far apart, causing coverage gaps. APs installed behind metal fixtures above ceiling tiles or next to dense materials like concrete walls may have their signals absorbed or reflected in unpredictable ways. Inconsistent placement, such as mounting APs at different heights or orientations in the same space, results in uneven signal distribution. These mistakes often produce performance complaints, even though the equipment itself is functioning correctly. Understanding how antennas project signal is key to designing effective coverage. Many assume wireless signals radiate in a spherical pattern, but in reality, they resemble flattened donuts. With an omnidirectional antenna mounted horizontally, the signal spreads out more on a horizontal plane than vertically. This means that placing an AP flat on a ceiling provides good horizontal coverage, but weak vertical penetration through floors. Directional antennas have narrow beams that must be aimed precisely. Without visualizing these radiation patterns, it's easy to create unintended dead spots or coverage overlap that leads to contention. Signal absorption and reflection are caused by environmental materials. Concrete, brick, and metal absorb wireless signals, weakening them as they pass through. Water and glass can reflect signals, scattering them and creating echo-like effects that disrupt communication. Even something as simple as a fish tank or a row of metal filing cabinets can alter RF behavior in a room. These effects are more pronounced at higher frequencies like 5 GHz, which are more easily absorbed or reflected than 2.4 GHz signals. Site surveys are essential for identifying these environmental factors before deployment. Channel planning in the 2.4 GHz band is challenging due to its limited number of non-overlapping channels. Only channels 1, 6, and 11 are spaced far enough apart to avoid overlap. Using adjacent channels, such as 2, 4, or 8, creates interference as the frequency ranges overlap and cause contention. This is a common problem in residential or dense office buildings where multiple networks compete for the same spectrum. Choosing non-overlapping channels is critical, and even then, the 2.4 GHz band can become saturated quickly in environments with many APs or neighboring networks. The 5 GHz band offers more flexibility with a greater number of non-overlapping channels. This allows better channel reuse, particularly in high-density deployments. However, some 5 GHz channels are classified as DFAS, dynamic frequency selection, and must avoid interfering with radar systems. APs operating on DFAST channels must vacate if radar is detected, potentially forcing clients to reassociate on a different channel. This behavior can cause momentary disconnections if not planned for. Still, with careful management, the 5 GHz band provides much more room for efficient, high-speed wireless networks. Interference from nearby networks remains one of the most persistent wireless design challenges. In apartment complexes, shared office buildings, or urban environments, dozens of Wi-Fi networks may overlap in the same frequency range. Clients experience slow speeds, frequent retries, and unstable connections. Site survey tools like Wi-Fi analyzers can show which channels are in use and help you select less congested ones. Visualizing spectrum occupancy before assigning channels prevents you from contributing to the problem and allows you to create a more stable network experience for users. Signal loss over distance is an unavoidable part of wireless physics. As a signal travels, it weakens, according to the inverse square law, meaning every time the distance doubles, the signal strength drops by a factor of 4. As signal strength decreases, the access point lowers the modulation rate to maintain reliability. This means that users farther from the AP may still be connected, but will experience significantly lower throughput. That's why it's important not just to cover an area with signal, but to ensure that the signal is strong enough for the intended application. VoIP and video streaming, for example, require stronger, more stable connections than email or web browsing. Another key design factor is load balancing across access points. A common mistake is assuming that simply placing more APs in a space will improve performance. However, if too many clients connect to a single AP while others remain underutilized, performance suffers. This often happens when APs are misconfigured, power levels are inconsistent, or placement does not encourage even distribution. Wireless controllers can assist with load balancing by steering clients to less congested APs or frequency bands, but physical layout must also support balanced coverage. Planning for client density is as important as signal strength in performance-sensitive environments. Another factor that significantly impacts wireless performance is antenna orientation. While access points may come with integrated antennas, many enterprise-grade models allow antenna direction to be adjusted or even replaced with external options. Improper tilt or rotation of antennas can create coverage blind spots or radiate signal in unintended direction. For instance, if an omnidirectional antenna is tilted on its side, it may put signal vertically rather than horizontally, reducing coverage across a room. Directional antennas, such as patch or Yagi designs, must be precisely aimed to ensure the beam hits the intended coverage zone. A small misalignment can mean the difference between strong, stable connectivity and complete signal absence. Channel overlap issues can be tricky to identify unless you use proper diagnostic tools. One sign of overlap is an increase in client retries when devices continuously attempt to send frames but fail due to collisions or interference. Another symptom is noticeable drops in throughput, especially when neighboring networks are active. Using a Wi-Fi analyzer or controller-based monitoring tool, you can inspect real-time channel usage and identify which access points are stepping on each other's frequencies. Once identified, you can manually reassign channels or adjust transmit power to reduce the area of influence and eliminate contention zones. Adjusting transmit power is another balancing act. Setting access points to maximum power might seem logical, but it often backfires. High transmit power can bleed signal into unintended areas, creating overlap, increasing channel contention, and attracting clients that should associate with a closer AP. On the other hand, too little power causes dead zones and unreliable coverage at the network edges. In multi-AP environments, each unit's power must be tuned to ensure reliable coverage without stepping on its neighbors. Transmit power should also be considered in the context of client device capabilities. Smartphones, tablets, and IoT devices may not be able to transmit as far as they can receive. Roaming problems are also frequently linked to placement and power configuration. When coverage areas don't overlap correctly, clients may lose connectivity during transitions from one AP to another. This is especially disruptive in real-time applications like VoIP or video conferencing. Inconsistent SSIDs across APs or mismatched authentication settings can confuse devices and cause failed connections. Designing for proper overlap, typically around 15–20% signal overlap between neighboring APs, and using fast roaming features like 800 and 2.11r can smooth transitions. However, roaming behavior is also dependent on client device logic, so testing with real endpoints is critical. The choice of frequency band has a major impact on coverage and performance. The 2.4 GHz band offers longer range and better wall penetration, but suffers from limited channel availability and high interference. The 5 GHz band delivers faster speeds, more channels, and less congestion, but has shorter range and is more easily absorbed by walls and obstacles. Dual-band support in both access points and clients allows networks to steer devices based on performance needs. For example, latency-sensitive applications should favor 5 GHz, while low bandwidth or distance-sensitive tasks may perform better on 2.4 GHz. Wireless design limitations are frequently tested on the Network Plus exam. You may encounter questions asking you to identify a coverage issue based on signal strength data, recommend a channel assignment based on a het map, or explain why a user's device can see an SSID but cannot maintain a stable connection. You'll also need to distinguish between signal strength and throughput, understand the effects of RF interference, and suggest appropriate antenna types or placement. These questions reinforce the idea that wireless troubleshooting begins with physical and environmental considerations, not just software or security settings. Several tools are essential when confirming wireless design issues. Heat map software helps visualize signal strength across physical space, showing where coverage is strong, weak, or overlapping. This supports better AP placement and power tuning. Wi-Fi analyzer tools, available as apps or software, show live SSID data, channel usage, and signal strength per band. Spectrum analyzers go deeper, identifying non-Wi-Fi interference from microwave ovens, cordless phones, or other RF sources. These tools allow you to match subjective user complaints, like the Wi-Fi is slow over here, to measurable signal behaviors that can be resolved. To summarize, the most common wireless design faults stem from poor placement, uncoordinated channel use, and a lack of understanding about how RF signals behave. Placing APs behind walls, choosing the wrong antenna type, or leaving channel assignment to auto mode can create serious problems for users. Likewise, ignoring environmental variables like metal shelving, elevators, or neighboring networks leads to frustrating performance degradation. Proper wireless design considers signal coverage, client behavior, and environmental obstacles together, supported by tools that validate performance before users start reporting issues. In every wireless environment, from small offices to large campuses, the RF behavior of your access points determines the user experience. Signal strength is only part of the equation. You must also consider SNR, channel reuse, antenna direction, and client density. The way access points are placed, configured, and tuned can either unlock reliable connectivity or lead to constant trouble tickets. Design is more than hardware. It's planning, measurement, and iterative testing. Knowing how to evaluate and improve wireless layout gives you the power to build faster, more stable networks. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.